Hello and welcome. In this video, we're going to talk about the first derivative, how to use the first derivative, what information it gives us about the original function, and that's going to tie to extrema, absolute and relative extrema. So our goal in this lesson is that we can find absolute and relative extrema and that we can determine the intervals on which a function is increasing or decreasing. So let's go ahead and jump in. Let's start off by defining what extrema are. So a relative extrema is a point or are points on a function that have the largest or smallest y values in a given neighborhood. So basically they are the peaks and the valleys. So you can see a relative minimum here because that is the lowest point in its general area. There are points lower than it on the graph, but in its neighborhood, it is the valley of that area. Similarly, there's a relative maximum here because this is the highest value in its general area, a relative maximum. We have another relative minimum here because it's the lowest value in its general area. So as you can see on this graph, there can be more than one relative extrema, more than one relative maximum or relative minimum. An absolute maximum or absolute minimum is the largest or the smallest y value over the entire function, and that will be on a specific interval. So we'll always be talking about on a closed interval what is the highest or the lowest value. So if we look back at this same graph, this value down here, the y value here, is not only a relative minimum, as we already showed, but it's also the lowest point anywhere on this graph. So it's the absolute minimum and the relative minimum. The highest value anywhere on this graph is going to occur at this coordinate up here. So that y value would be the absolute maximum of this function over this given interval. One thing I want to point out is that relative extrema are never going to occur at an endpoint, which should make sense because we're saying that it has to be the highest or lowest value in a neighborhood, and at an endpoint, there isn't a neighborhood. There isn't any area to the left or to the right in order for that to happen, as opposed to an absolute extrema, which could occur at an endpoint. So before we add a layer of calculus to what we're talking about, let's just look at the graph of a regular function and identify the key components that we're mentioning and going to need for the rest of this section. So here we have a graph of a function. Let's go ahead and identify some key components that we already know to be true about this function. So first, let's talk about where this function is increasing and where it is decreasing. And that literally just means if I'm tracing the graph from left to right, am I going up or down? So if I start at this arrow and I am tracing the graph from left to right all along here, I'm going up. Then when I get to that value, I start going down and I keep going down until I get here. Once I get here, I start going up again. And in Algebra 2 and pre-calculus, you talk about this as intervals in which a function is increasing and decreasing. So we can go ahead and write that. When we're writing those intervals of where it is increasing and decreasing, that's going to relate to x. So this function is increasing from negative infinity until we get to the x value of this point. Then it starts decreasing, so negative infinity to negative 1.54919. And it starts increasing again here at positive 1.54919. And then it is increasing forever since there's an arrow, and that's going to be to positive infinity. So we can identify where the function is increasing because simply it has a positive slope. It's going upwards. Similarly, it's decreasing when it's going downwards. So starting at x equals negative 1.54919 and ending at x equals positive 1.54919. That is the interval on which the function is decreasing or the slope is negative and it's going downward. Now we can tie in the relative extrema vocabulary that we just identified. There are relative extremas happening at each of these coordinates. Now that is where they are happening. When x is equal to negative 1.54919, there is a relative maximum because this is the highest point in its given neighborhood. The maximum, though, is the value of y there. So there is a relative maximum of 5.9489 when x is negative 1.54919. Similarly, there is a relative minimum of the y value when we are at that indicated x value. So the maximum and minimum is the value, aka the y, when we're at a particular x. Now here, this function goes on forever, which means there aren't necessarily an absolute maximum or minimum because that's only guaranteed on a closed interval by the extreme value theorem. If we have a closed interval, then we have a maximum and a minimum. If we don't have a closed interval, like we don't have one in this graph, the graph goes on forever and ever, so it's going down forever and up forever, which means there aren't absolute extrema. So how does this tie to what we have been doing in calculus? Well, what we just said is that when the function is increasing, the slope is positive, and we know that slope is derivative. When the function is decreasing, the slope is negative. So let's see if we can tie this idea of slope or how the function is behaving to the derivative. All right, as we have mentioned, the derivative is the slope of the tangent line. So if we have a function and the function is increasing, that means the derivative must be positive. So if the derivative is positive, the original function must be increasing, meaning the function from left to right is going up at that specific value. Every tangent line along this curve would be positive because the function is increasing. Similarly, if the derivative is negative, that must mean the original function is decreasing anywhere or on any interval that the function is negative. The function decreases when the derivative is negative. If we are changing, I want you to notice something in that picture right here. I changed from increasing to decreasing. If I changed from decreasing to increasing, that's going to create a relative extrema. And it's going to be a different type of relative extrema based on what we're doing. So what we just saw is when we changed from positive or from increasing to negative, so when the derivative changes from positive to negative, we have a relative maximum. When we are changing from decreasing to increasing, we have a relative minimum. There's a special name for these values where we are changing besides just being relative extrema. There's a special name for what's happening in the derivative there. So if the derivative is positive, it's increasing. If the derivative is negative, it's decreasing. So what's happening to the derivative when it's changing? At that moment, the derivative or the slope is going to equal 0. And that has a special name that's called a critical number. So a critical number is the value in which the derivative is 0 or where it's undefined. So the derivative gives us a ton of information about the original function. So all the information that the derivative gives us tells us about the original function. It tells us where the original function is increasing, where the original function is decreasing, where we have relative extrema, and that's really valuable information. So when we're thinking about an original function, if we want to identify this behavior, we're going to find the derivative, and we're going to look at where it's changing sign, where it's positive, where it's negative, and where it's 0. And that's going to allow us to find a lot of useful information. So let's look at an example. Okay, so we're going to look at an example where we already have a derivative. So we don't have to worry about taking the derivative. We're really going to focus on using the derivative on this problem. If we want to find the critical numbers, that means we're looking for where the derivative is 0 or where it is undefined. Well, this is a quadratic. A quadratic is defined everywhere. So we're just going to set it equal to 0. Where does this quadratic equal 0? Well, this quadratic is going to equal 0 if x is equal to plus or minus 2. So I'm going to come over here, and where it says CN, that stands for critical numbers, I'm going to go ahead and write plus or minus 2. Now what we're going to do is we care about where the derivative is positive, where the derivative is negative, and where the derivative is 0. So what I'm going to do is I'm going to make a number line or a sign chart for my derivative. I know that my derivative is 0 at positive and negative 2. So those are the only places where it could potentially be changing direction. So what I want to know is, What's happening in my derivative over here if we're smaller than negative 2? What's happening in my derivative if we're between 2 and negative 2? What's happening in my derivative if we're greater than negative 2? So we're going to plug in numbers that are smaller, in between, and greater than these two critical numbers so that we can identify if the derivative is positive or negative over those individual intervals. So let's go ahead and look at this. What's a friendly number, a number that's nice to plug in that's smaller than negative 2? So maybe something like negative 3. And we're going to plug this into our derivative. So if I plug this into this derivative up here, negative 3 squared is 9. 9 minus 4 is 5. I actually don't really care that it's 5. All I care is that that number is positive. So I'm going to go to my sign chart. I know every number smaller than negative 2 will give me an output in the derivative that's positive. Then I'm going to ask myself, what's a friendly number that's in between negative 2 and positive 2, like 0? If I plug in 0 to the derivative, I get 0 squared minus 4, or negative 4, which means every x value in between 2 and negative 2 is going to give me a negative output. Lastly, we need to plug in a number into our derivative that's greater than 2, like 3. That's going to give me 9 minus 4 again. That's going to give me a positive number. Now, you don't explicitly need to show this work. It could happen in your head. You don't need to simplify it down to be a number. All we care about is if we get a positive or a negative value. And now that we have this sign chart is going to give us so much valuable information. Everywhere that our derivative is positive, that means the original function is increasing. So that means everywhere smaller than negative 2 and everywhere bigger than positive 2. And our justification for that, how do we know that, is simply because the derivative is positive on those intervals. Similarly, in between negative 2 and positive 2, the derivative is negative. If the derivative is negative, that means the original function is decreasing. So on the interval from negative 2 to positive 2, the original function is decreasing because the derivative is negative. Now, we talked about how our function changing from positive to negative or from negative to positive is going to create an extrema. So if my function is increasing and at x equals negative 2 it starts decreasing, what we have just created is a relative maximum. It was going up and then it started going down at x equals negative 2. So there is a relative maximum when x equals negative 2, since the derivative f prime changes, I'm going to use delta to represent changes from positive to negative. It was going up and then it started going down. That means we're going to have a relative maximum. Similarly, at x equals positive 2, the function was going down and then it starts going up. That's going to create a relative minimum when x is equal to positive 2, since the derivative f prime changes from negative to positive. So we're not only identifying the key pieces of information that the derivative is telling us, but we're justifying how we know that gives us information about the original function. So really, we're going to focus on this a little bit more in the next couple of examples. I want to point out we don't actually know what the maximum or minimum value are in this problem because we started with the derivative, which means I don't know what happens in the original function when I plug these two x values in. But the next few examples we look at, we will start with the original function. So let's keep pressing on. Okay, here we have a summary of what we just did. The very first thing we're going to do is we're going to either find the derivative, or if it's already given, we're going to use the derivative. And we're going to identify any critical numbers. Where is the derivative, 0 or undefined? Also, pay attention, every once in a while you might have an issue in the domain in the original function, and that needs to come into play on your sign chart as well, and we'll talk about that on one of the examples. After you find those critical numbers, you're going to make a sign chart or a number line where you're plugging in the values to figure out where the derivative is positive or negative. Remember that you're plugging these numbers into the derivative. From that number line, we can determine where we're increasing, decreasing, and where we have relative maxes and mins. So let's look at some more examples. Here we have the original function, a cubic function. What I'm going to have you do is pause the video and go ahead and find the derivative and set it equal to 0. That way you can find those critical values. Then unpause the video and see how you did. Okay, hopefully you were able to work through that. We found one and only one critical number, and that is x equals 1. Now, I want you to create a sign chart with your derivative. The only number that's going to go on that sign chart is 1. So plug in something that's smaller than 1, like 0. Plug in something that's bigger than 1, like 2, and go ahead and figure out what happens in your derivative. Remember, you're plugging these into your derivative to determine the sign chart for your derivative. Okay, when we plug in 0 and when we plug in 2, we get positive numbers. We actually get 3. So what does this mean about our function? Well, we see plus signs on our sign chart. That indicates that we are increasing, and we're actually increasing everywhere. There is no interval that says decreasing, so this function is never decreasing, since the derivative is never negative. Or we could say f prime of x is never less than 0. Now, we can write that it's increasing everywhere. At 1, we did identify that the derivative is 0, but everywhere, not including 1, the derivative is positive, or it's non-negative, if you feel more comfortable saying non-negative. This should make sense to us. We're looking at a cubic function. Cubic functions typically look like some variation of this. So this is always going up, and at some x value, 1, we just found that x value, it's sort of shifting what it's doing, but it's not shifting the fact that it's increasing. What this also means is that we don't have any relative extrema since the derivative doesn't change sign. So this is sort of a simple and confusing one all at the same time. We found the derivative, we found where it was positive, we found it was never negative, which means it's always increasing, and there aren't any relative extrema. Let's look at another example that has different types of intervals. Okay, just like last time, I'm going to encourage you to pause the video to find those critical numbers on your own. Identify for yourself what property you're going to use in order to take this derivative, and then unpause the video and see how you did finding your critical numbers. Okay, so when we find the derivative, we find 2/3 times x squared minus 9 to the power of negative 1/3 times the derivative of the inside. That's the chain rule. And I'm going to rewrite that as a fraction. This fraction is going to be 0 when the numerator is 0, so we have a critical number at x equals 0 because that would make the numerator 0. This fraction is going to be undefined, or the derivative is going to be undefined if the denominator is 0, and the denominator is going to be 0 if x is plus or minus 3. So remember, critical numbers are where the derivative is 0 or where the derivative is undefined. Now we're going to make a sign chart. We're going to include all of those values on our sign chart. I want you to go ahead and pause the video, work through your sign chart, and then see if you can write the increasing and decreasing intervals. So here's my sign chart for my derivative, and notice I didn't actually find the values. I just figured out if the numerator and the denominator were both negative, both positive, or one of each, because all I care about is the derivative positive or negative? This means we are increasing from -3 to 0 and from 3 to infinity, and this is true since our derivative is positive. Or you could write since f prime of x is greater than 0. We are decreasing everywhere that our derivative is negative, so negative infinity to -3 and 0 to 3 since f prime is negative, or you could write f prime of x is less than 0. Thinking about extrema, we are going from decreasing to increasing, so there's a minimum here. From increasing to decreasing, there's a maximum here. From decreasing to increasing, there's a minimum here. Now, since we have the original function, we can actually plug those values in to figure out what the maximum value is. So if we plug in -3, we're going to get 0 if we plug that into our original function. If we plug in 0, we're going to get -9 to the 2/3 or 81 to the 1/3. That's not going to be an integer, so I'm just going to leave it like that. If we plug in positive 3, we're going to get 0 again. So this question doesn't ask us for what the maxes are, but these are our relative minimums at 0, and 81 to the 1/3 power is our relative maximum. So we have a relative maximum when, that's how I know I'm just writing the x value, x equals 0 since f prime changes from positive to negative at x equals 0. We have relative minimums, we actually have more than one, when x is plus or minus 3 since f prime changes from negative to positive at x equals plus or minus 3. All right, we're going to complete one last example on increasing, decreasing, and relative extrema before we quickly talk about absolute extrema. I'm going to encourage you to try and complete this problem on your own. I'm going to give you one hint. If you look at this as is, you might be thinking that you have to use the quotient rule, and that's true, but you could also split this into 2 fractions, and then you would get x cubed over 3 plus 1 over x, or x to the negative first power, and I think that might make the derivative work a little bit easier. You can choose to do it either way, but see how far you can get if you can get all the way through this, and then unpause the video and see how you did. So here's my work for the derivative. I want to point out in the original function, g, x is not allowed to be 0. I want to include that on my number line because there's a vertical asymptote there. So I want to make sure when I'm saying my intervals of where we're increasing and decreasing that I'm not including 0. I have to stop before and after 0 because g, the original function, doesn't exist there. That's going to add a little bit more work when we're making our sign chart, but I think you can handle it. So here's the sign chart. Now I'm going to go ahead and write my intervals for increasing and decreasing. Make sure for decreasing, even though it's decreasing both before and after x equals 0, make sure you exclude 0, again, because you can't plug 0 into the original function. Lastly, we're going to talk about extrema. If we change from increasing to decreasing, there's a relative maximum when x is equal to -1, since our derivative, not f, but g prime, changes positive to negative, and there's a relative minimum at x equals +1, since g prime changes from negative to positive. Again, if we wanted to find those relative max and min values, we would plug positive and -1 back into our original function g, and that would give us the max and min values, the relative extrema. Not just where, because that's what we really have found. We found which x values they're occurring at. We're going to talk about absolute extrema, and then we're going to go ahead and wrap up this video. So we already talked about what an absolute extrema is, but what we're going to do now is we're going to actually talk about finding them. It's going to be less work than what we just did with our relative extrema. We're going to start in a really similar way. When we're finding the absolute extrema, we have to remember that this could happen at an endpoint. So in our example here, we're given 2 x values. And the only other place it could happen, besides at the endpoints, is at any place where there was a relative extrema. So we're going to start by finding the derivative and setting it equal to 0. Then instead of making a sign chart, we're just going to make a table, and we're going to plug those values into our original function and figure out what's the biggest number and what's the smallest number. So go ahead and find your derivative and your critical numbers, and then unpause the video and see how you did. So we should get that our critical numbers are 0 and 4. 4 is not inside the interval from -1 to 3, so we don't have to worry about that. The next thing I'm going to do is I'm going to just make a table with my candidates. There are 3 possible values for the absolute max and min in this problem. The 2 endpoints, so -1 and +3, and any critical number in between them, 0. Now, I'm going to plug those back into my original function and find their outputs. Go ahead and do that on your own. Here are those values. And now we're going to identify the largest, which is 0, and the smallest, which is -9. So we can say f has absolute max of 0 and absolute min of -9. On the interval from -1 to 3. Let's look at another example. So go ahead and try this out on your own for number 4, and then I will work through number 5 with you. So here's our derivative, set it equal to 0. The only critical number that we're going to get is 1, but also the derivative is going to be undefined if x is 0. And now we're going to plug those 4 values into our original function. And from the outputs, we can identify the absolute max and min on this interval. And there we have it. In a previous chapter, we talked about how we could rewrite absolute value as a piecewise function. This absolute value function, if we graphed it, it has a vertex at x equals 2. So that's where we're going to split our piecewise function. We're going to split it at 2. And it only goes from 0 to 5. If we are less than 2, we're on the negative part of that line. So that would be negative x plus 2. If we're on the positive side, we're here. So if we find the derivative now, we're just going to take the derivative of each of these pieces. The derivative of that top piece is negative 1. The derivative of the bottom piece is positive 1. Since these are not the same, that means we won't have any or equal to's with our derivative. So the derivative is undefined at x equals 2. Because at x equals 2, that's where we should be switching from one piece to the next, and the derivative is not the same. So the only critical number is x equals 2, and then we need to also consider the 2 values, our endpoint. And then we can plug those 3 values in. The absolute value of 0 minus 2 is 2. The absolute value of 2 minus 2 is 0. The absolute value of 5 minus 3 is 3. So our absolute max is 3 and our absolute min is 0 on the interval from 0 to 5. And there we have it. Let's go ahead and wrap up this video. All right, in this video, we talked about how to use the first derivative to find relative extrema and to find the intervals on which a function is increasing and decreasing. And then lastly, we use the candidate test to find absolute extrema using the derivative and the endpoints of a closed interval. Go ahead and write down any questions you have, and I look forward to supporting you. Thanks for listening.